Good morning, everyone. Now we are recording. I'm going to call up slides. And I understand that you're not having lecture again this week. So I'm going to try to do a whole week's worth of material today for chapter 27, all this material here. I'm going to try to get through and point you to how to do this week's homework. So let's jump right in. The chapter begins with the discussion of the discovery of an electron. So in the late 1800s, people were doing things like this. Here is a glass tube thing, and inside there's a wire of metal with a little platform there that's connected to high voltage like this with the anode over here. So cathode is the one that's negatively charged, and the anode is the positively charged one. And people notice that if you put a very high voltage, first of all, you take the air out of this glass thing. So this is as good as a vacuum as you can try to get. And then if you put high voltage here, people notice that this end of the glass tube would start to glow. And if you put screens in between, they notice that they could sort of block some of it, and a smaller area of the glass would glow over here. So that suggested that there was some sort of beam of some sort that was coming out of the cathode. Thomson, J.J. Thomson, had an apparatus that looked like this. So this part of it is just the same thing that I just showed you before. And by the way, since these were sort of ray things that they didn't know what it was, they called them cathode rays, because it came out of a cathode. So J.J. Thomson had one of these cathode ray tubes over here. And then he set up over here, notice that you've got plates, parallel plates over here. This one is positively charged, see? So it's connected to some circuitry, so that this ends up positively charged and that one negatively charged. And at the same time, there are these wire coils on each side, and that lets you create a nice uniform magnetic field in between if you have current going through. So he did these experiments with this. He had this high voltage in place so that it produced these cathode rays. And if neither the electric field created by these plates, if that was not there, or the magnetic field created by these coils of wire, if those were not there, the cathode rays would just go straight through, and this part of the bulb over here would be bright, would light up, would start to glow. If you put a voltage across the plates so that there was an electric field there, he could deflect them. And it turns out that with the upper one charged, this part of the globe over here, of the glass over here, would be the one that glowed. And if you had a current going through in these, if he then turned off the electric field and put a current through these coils, he found that he could deflect them this way. So from this, he concluded that whatever it was that these cathode rays were, they were negatively charged things. In the homework problem, they ask you to consider the equations that the equation for the force that an electron, we know that these are electrons nowadays, the homework problem asks you to consider the force that this electric field exerts on the electron and the force that the magnetic field exerts on the electron, because the electron is going through a magnetic field. And that's described exactly in the first part of the book. I won't go through it with the equations, but you can balance those equations and you can say something about the ratio of the mass to the charge of an electron, which Mr. Thomson did. Okay, so for the first homework problem, I refer you to the first section of the chapter. It's explicitly there. Okay, let's go on to the next thing. Here was a mystery from the end of the 1800s or so. There was this concept of a black body. So the idea is that everything radiates electromagnetic energy. More so if it's at a higher temperature. So you and I are radiating more or less in the predominantly in the infrared region. Maybe you've seen sort of security camera footage where the camera is sensitive to infrared, and so you can see the temperature of somebody, and if they walk across the floor without shoes, you can see where they heated up the floor, etc. So everything is radiating electromagnetic radiation. We're not usually noticing it because things are not radiating predominantly in the visual range. However, perhaps you've seen a stove, and when you turn on the stove, with maybe an electric heating element, when you turn that on, it starts to turn red, right? It heats up and it starts to turn red because it's glowing. So it's radiating electromagnetic radiation in a different part of the spectrum, starting to radiate in a region where we could see it. So the concept of a black body is just a thing that will absorb all electromagnetic radiation and also radiate at all wavelengths. That's the idea of a black body. It's a terrible name because such a thing is not black. It's black in the sense that it absorbs everything, but it also radiates at all wavelengths, so it would be white. So what is it? Okay, so it's an object that is radiating. It turns out if you study the spectrum of radiation that comes out of things, it looks like this. So here's a graph of the intensity of the radiation coming out of an object versus the wavelength of that radiation. So it's like tells you what the spectrum is. And you see it depends on the temperature of the object. Here we're talking about rather hot things, so 3,000 Kelvin, 4,500 Kelvin, 6,000 Kelvin. And notice that the visible range of light, of the light that's radiated, is only over here. So here's an important relationship, and one of the homework problems asks you to just plug numbers into this one. This is, I think it's pronounced Wien's law. The peak of this distribution is related to the temperature of the object in this way. The peak wavelength times the temperature is this particular number. So you see the peak here is there, and then for colder, it's a little bit higher in wavelength, and higher in wavelength even more. You may recall, I don't remember if we discussed it, but in chapter 14, there's this thing called the Stefan-Boltzmann law. And that tells you something about the total intensity, which is the area under these curves. So all of the intensity that's radiated by an object, that's related to temperature of the fourth power. Sigma here is a particular number. Anyway, that's why these curves look like this, why the green one is so much higher than, say, the red one. It turns out that the areas underneath, they change this way. Okay, but again, here's another picture that shows you the visible spectrum here, and with similar temperatures. You and I, at sort of room temperature, the spectrum would be very flat over here, and it would peak somewhere over here in the infrared, and so we basically wouldn't see anything. But the heating element starts to warm up, and it starts to rise up here in the red, and that's why it starts to turn red. If something gets really, really, really hot, it starts to get sort of whiter, right? Because the curve comes up and it picks up yellow and orange and red together. But remember, we're at 300 degrees Kelvin or so, right? And so those curves would be very flat on this graph. But look at this one. This one is about 6,000 Kelvin. Notice that it has predominantly green yellowish, a lot in the yellow. What is a thing that radiates a whole lot of yellowish light? The sun. And this is why we know that the sun has a surface temperature of something like 6,000 Kelvin. A little bit less, so that the maximum is a little bit closer into the yellow. And then when something is really hot, it starts to radiate predominantly in blue. But notice that it's picked up a whole lot of visible spectrum, so it's going to look pretty white, maybe bluish white. Okay, so what is the big mystery with this? The big mystery, called the ultraviolet catastrophe, is that classical theory could not explain the shape of these curves at all. Well, it could capture the right side more or less. The ultraviolet is down here. This is the the infrared on this end, and the ultraviolet over here. Classical theory says that if you consider just an object, a black body that radiates, it should radiate an infinite amount of radiation at low wavelengths, which clearly is wrong, makes no sense. And experimentally, you see the curves turn over and they come back down. So that's why this was a catastrophe. The theory was just completely wrong, the best theory that we had. The attitude at the late 1800s was, nah, we'll figure it out. It's just a couple of details we need to clean up. No worries, we've figured out all of science already. But still, it was a persistent problem. It's completely wrong. Enter Max Planck. So Max Planck made a contribution, which I will describe shortly, which is credited to be the birth of quantum mechanics. Perhaps you've heard of quantum mechanics. And so it has a particular birthday, December 14th, 1900. Mark it on your calendar and celebrate it every year. There is Max Planck when he was an older man. His contribution was in late 1900s, and so it became well known in the 1901 or so. And this is what he looked like in 1901. I find this picture really amusing because look at how harried he is, and it makes sense that he was pulling his hair out to try to figure this out. But he was able to come up with a theory that matches the data really, really well, as you can see here. The thing about the theory was that it had a completely crazy idea. The idea is that the energy of the atoms that make up the black body, or whatever object is radiating, is discrete and not continuous. Classically, you would imagine that the atoms are moving back and forth, and if they're cold, they're moving a little bit, and if they're hot, they're moving a lot. And so you can have whatever energy you want in these things. But Planck is telling us no, the energies in those molecules can only take on discrete values, particular values. And he listed what they were. They were integer multiples of a number times the frequency of the oscillation, as they oscillate. And h is a number which is now called Planck's constant. So the particular number, and we'll use it. So that's the assumption that goes into the theory, which leads to this beautiful matching to the data. There it is. There's a Max Planck's constant. It has units of joule seconds. This is shocking. Are you shocked? Here's the analogy the book gives you. You can imagine you could put a crate on an inclined plane. And classically, you could put it wherever you want. Quantum mechanically, so classically, the potential energy of this thing could be whatever. It's just a continuous function of height. But quantum mechanically, Planck says, no, you can only put it at discrete heights. So the potential energy only has particular values and not a continuous value. It has certain quantized values of energy, the potential energy of this crate. That seems quite reasonable. It's just telling you that nature is not a smooth inclined plane, but rather something with steps. So I don't know. This is a very good analogy. I like it a lot. It's not really shocking, though. And I didn't have time to draw. This is not shocking. I didn't have enough time to draw a pendulum. But imagine a pendulum swinging back and forth. It does so nice and smoothly, and you can imagine that I could give it whatever energy I want, so that it would swing, from whatever angle I want to the other angle. If I want a big angle, I'd give it more energy. If I want a little angle, I'd give it less energy. Well, quantization suggests that no, I can only have it oscillate at particular discrete values of the angle. That's pretty shocking. And furthermore, the pendulum can only take on certain discrete values of the angle. So what does it mean to even swing back and forth? Later on in the development of quantum, they figured out that a simple harmonic oscillator cannot even have zero energy. It has to have at least a little minimum energy called a 0-point energy. All right, so hopefully that has shocked you somewhat. Let's go back to Planck's explanation. So he said that the energy in the atoms of the object can only take on these discrete values. And if you make a sort of graph like this, where you plot vertically these little level bars telling you energy values, so you have n equals 0. In this case, we have 0 energy here. And when n equals 1, you have this energy, etc. So these are the only allowed energy levels for the atoms and atoms and molecules in the object. Well, it's in terms of the frequency of the oscillation, and remember for any wave, the wavelength times the frequency is the speed, and we're talking about electromagnetic radiation being absorbed and radiated. So we can plug this in and express those energy levels in terms of the wavelength like this. So in this formulation, you see that the space between these levels is equal to this amount here, hc over lambda. In particular, it's inversely proportional to the wavelength. The spacing between these energy levels that are allowed is inversely proportional to the wavelength. So if the wavelength is large, that means that the spacing between these energy levels is small. And so your graph would look like this. The little spacings are very, very close together. And they're so close together for very large lambda that they're essentially continuous. So that the molecules could take on almost any value in this range. Just, approaching classical theory. Right? The larger lambda is, the closer you get to a continuous spectrum. And that is why classical theory can explain this part of the curve for larger wavelengths. This side of the curve behaves like classical theory suggests, because the energy levels are so close together that you basically can't tell that there are spacings. On the other hand, if you have small wavelengths, then this level spacing is big. Right? The denominator is small, then this number is big. And it's very unlike classical theory. You have very big spaces between and very, very clearly distinguished energy levels for the atoms and molecules. And so this side of the curve is not well described by classical theory. This side of the curve must be explained in terms of these level spacings, which are quite significant. And that's what Planck was able to do. And look how good the fit is. It's remarkable. So nature was trying to tell us something. The vibrational energy of atoms and molecules in an object is not continuous. They can't take any old value. Those energies occur in discrete chunks. And so that's the quantum of energy. So that word comes from the same root that quantity comes from. The quantum of energy is that the idea that energy comes in just chunks. A quantum of energy is sort of the minimum chunk of energy. Planck called this an act of desperation into which he was forced. He's quoted as saying a theoretical explanation had to be found at any cost, whatever the price. And so that's why he was pulling his hair out. He himself thought that it was absurd. Even though his theory worked extremely well to explain the data, he thought it was just absurd. And he kept looking for other explanations that made more sense to him. Enter Einstein a couple of years later. So Einstein, in 1905, in addition to presenting the special theory of relativity, in addition to explaining Brownian motion and therefore establishing once and for all the molecular atomic theory of matter, which was still controversial back then. In addition to all of that, he also explained the photoelectric effect using this idea of Planck's. Einstein went on to win the Nobel Prize. He did not win it for relativity. He did not win it for explaining Brownian motion. He won it for the photoelectric effect explanation. All right, so what is the photoelectric effect? Let me get a bit of water.
So Planck never got a Nobel Prize?
Oh, yes, he did.
Oh, okay, good.
Yes, he did. No worries. Here's the photoelectric effect. It was discovered by Mr. Hertz in 1887, same guy that you named the unit Hertz after, and the same guy who was the first to detect electromagnetic radiation. So a photocell is basically a glass bottle that's you take all the air out of, and then once again you have an electrode on the inside and another one on the other side. You hook up a battery to it. It turns out that if you shine light on this metal, and the circumstances are set up correctly, electrons get ejected from that metal. And if you have a battery set up like this, those electrons get attracted to this electrode at C, and it completes the circuit, and in this ammeter you start to see a current flowing. If you turn off the light, these electrons do not get ejected, and the current does not flow, and you don't see anything in this ammeter. So no light, you don't see a current. With the right circumstances and with the right light, electrons get ejected from that plate of metal P, and it completes the circuit, and you measure a current. You can measure the maximum kinetic energy of the ejected electrons by adjusting this voltage. The idea being that light comes in and kicks out the electrons, and then they're moving around with some amount of kinetic energy. Imagine a guy standing in a field kicking soccer balls. The soccer balls are all just sitting there, and he goes around and kicks them. And he kicks them all with exactly the same amount of energy in various directions. Well, you could imagine setting up a battery here, and with the analog to that would be you're setting up sort of an inclined plane in the middle of the field, and when the guy kicks the ball starts to roll uphill, right? If you adjust the height of that incline, you could measure the maximum kinetic energy of the soccer balls, right? Not every soccer ball will be going straight up the incline, but those that do, if you have the incline at the right angle, you could set it up so that the soccer ball goes right up to the very top and then stops. A little bit lower angle, some of them go up and go through, and you measure a current. At the right angle, they don't make it anymore. Right? In this case, this voltage is analogous to that inclined plane angle. So that's how you could measure this maximum kinetic energy of the ejected electrons. So when you set up a voltage so that you then no longer detect any electrons, that's called the stopping potential, that voltage. All right, what does classical theory say about this? Classical theory says that this is a material made out of molecules that jiggle around, and when the electromagnetic radiation, which is light, comes in, it takes those electrons and starts to move them back and forth, depending on what the wavelength and frequency of the light is. So if you increase the light intensity, that means, remember, intensity is proportional to the amplitude. That means that these electrons get moved back and forth with a bigger amplitude. So classically, you would expect to have more ejected electrons, be able to rip them out more because they're made to oscillate more. So therefore, you would see more current. Furthermore, once they are ripped out, if you have higher intensity, you would have higher kinetic energy in those released electrons. Classically, the frequency of light should not matter, because whatever frequency of light is going to make the electrons move back and forth. Oops, there we go. Einstein came around, and what he said was the following. Using Planck's idea of quantization, in particular saying that light is not an electromagnetic wave, but rather is a bunch of little discrete particles of energy called photons, he explained it like this. According to Planck, this is what the energy of the photon is. It depends on the frequency or the wavelength of the light. H and C are constants, right? Planck's constant speed of light. Einstein said that when a photon is absorbed by the material here, it just disappears. And its energy gets split into two parts. Some of the energy goes into liberating the electron from the material. That amount of energy is called the work function. It's an amount of energy that depends on what the material is. If there's any leftover energy, that becomes the kinetic energy of the liberated electron. And so you have this relationship. Here is the energy of the photon that comes in. Some of it goes into liberating the electron. That's this work function, W0. And whatever energy is left over is the kinetic energy of the liberated electron. By the way, sometimes the work function is a phi. Okay, so given that picture that Einstein described, more light intensity corresponds to more photons, but each photon still has the same energy. So since all the photons have the same energy, assuming that we're using a single wavelength of light, which you can do, then the kinetic energy of the ejected electrons doesn't change with increased intensity. The light is just a bunch of little packets of all the same energy. So when one of those photons is ejected, you still have the same breakup of that energy. And so the ejected electron still has this amount of kinetic energy. If you have greater light intensity, you just have more ejected electrons, but they all have the same kinetic energy once they're ejected, according to Einstein. Furthermore, there's a minimum frequency of light below which you don't eject any electrons, right? The photons must have enough energy to liberate the electron. That's the work function. If they don't have that much energy, then they don't liberate any electrons, according to Einstein. So there's a minimum frequency of light that would cause electrons to be ejected. So here's the contrast. This is what classical theory says, and here's what Einstein said. They are vastly different predictions. Tremendous. It's very hard to come up with theoretical predictions that are so drastically different than this. Well, experiments prove that Einstein was actually right. Of course, he's Einstein. In particular, experiments made by Robert Millikan, surprisingly, many years later, 1913, 1914. So the inescapable conclusion from this experiment and this theory is that light behaves like particles. Light occurs in discrete chunks of energy. If you understand what I was describing about Einstein's explanation of the photoelectric effect, you cannot conclude anything else. Light is like particles. Here's an aside. We've been measuring energy in joules. Another unit of energy is the electron volt, which we've seen before, but I want to remind you that an electron volt is the energy gained by an electron when it is accelerated by a potential difference of 1 volt. So here's the equation that tells you what that energy is. You put in the charge of an electron for Q, you put in 1 volt over here, and the energy is then 1 electron volt. So 1 electron volt equals this many joules. That's a useful thing to have for this chapter. Okay, so let's, I guess I don't really have time to do this, but I'll leave these slides here where I do a little problem going over the work function and the stopping voltage for this. So I'll have a look at these slides later. Sorry about this, but there's so much to do and there's just so much time left. All right, so now we are left with the question, what is light? And notice that I'm emphasizing the word is. What is light? Remember Young's double slit experiment? And you put light through 2 slits and you got a diffraction pattern? How could you possibly explain that without saying that light behaves like a wave? Right? Inescapable conclusion. Photoelectric effect. Inescapable conclusion, light behaves like a particle. So which is it? Well, of course, nature does not have to conform to our paucity of ideas. Light is light. Sometimes it behaves like a wave, sometimes it behaves like a particle. It seems very mysterious to us, but that's, that's our problem. It's not nature's problem. A couple years later, Louis de Broglie, French guy, he came up with the idea that maybe particles like electrons, right, the light, which we think of as a wave, behaves like a particle. Well, maybe things like particles actually behaves like waves. So maybe electrons can behave like waves. And actually, we already saw in the earlier chapter that you could make diffraction patterns with electrons. That was already described at the end of whatever the previous chapter was. By the way, this was Louis de Broglie's PhD dissertation that he had to defend in front of Einstein. Einstein approved, however. So maybe particles like electrons behave like waves. They do. As we have seen, you can actually cause diffraction with electrons. And what de Broglie did is he wrote down an equation for the wavelength of a particle. So the wavelength of a particle that has momentum p is given by this, where h is Planck's constant. So now you're left with the question, what is matter? You're thinking of matter as a bunch of particles. Well, what is it? Maybe it's kind of wave-like. What is it? Something mysterious. Okay, I would like to do this problem, 2747, out of the homework for this chapter because it involves a bunch of these ideas that I just described, and is maybe the most difficult problem in this set. We need 3 things to do this problem. Well, first let me read the problem. What voltage is needed to produce electron wavelengths of 0.51 nanometers? So we're going to take electrons and we're going to accelerate them across, say, 2 charged plates. So there's a potential difference. We'll accelerate them. We'll give them some momentum. And we want to give them just the right amount of momentum so that according to de Broglie's equation here, we have the given wavelength that we want, which is 0.51 nanometers. We have to assume that the electrons are non-relativistic. I guess you're skipping the relativity chapter, which is kind of unfortunate, but understandable given time constraints. All right, to do this problem, we need these elements. So first of all, an electron accelerated through a voltage V gains this much energy. I've already showed you that. The de Broglie wavelength of a particle momentum P is this. And classically, the energy, kinetic energy of something is 1/2 mv squared. So these three elements are enough to answer this question. Relativistically, we would have to use this equation instead of that equation. So if we know that the electrons are going at a speed comparable to the speed of light, this equation for the kinetic energy no longer applies. Instead, you have to use this equation. It gives you the energy in terms of the momentum and the mass. Have a look at this equation. Notice that if you're considering a particle that does not move, it does not have any momentum, what do you get? E equals mc squared, the famous equation, telling you that mass, m, is energy. E, certain number of joules are in certain number of kilograms of mass. The constant of proportionality is the speed of light squared. Okay, but anyway, I had to throw that in because we want to use this equation later. In this problem, we're going to assume that the electrons are not relativistic. So we'll just use these elements. All right, let's start with the energy, the kinetic energy here. I want to express it in terms of momentum. So I'm going to multiply the top and bottom here of this fraction by mass. So I could write down mv squared with the square inside of parentheses, the mass inside of parentheses there. And so I could replace that with the momentum. So the energy expressed in terms of momentum, p squared over 2m. Momentum from de Broglie is just this. I solved it for p. And if I combine these, then I have the energy in terms of h, the mass of the electron, in this case electron, I put the subscript e, and the wavelength that we want. So this energy, I'm going to set equal to the energy that's gained by the electron when it goes through a voltage. Like this. And now I have QE. So I can solve that for the voltage, and we get that answer. So with this formula, we can answer the question. We just plug in the numbers on the right. Right, so those are the three elements that go in. You combine these equations, you get this. Plug in the numbers like this. There's Planck's constant. Here's the mass of an electron. Here's the charge of an electron. And here's the wavelength that we want. It's given in the problem. We get the answer, 5.79 volts. You might be wondering, how do we get from these weird units to volts? And I have spelled that out for you, but I won't go over it now in the interest of time. But ultimately, the answer is 5.79 volts. So please review this later so you can see how the units work out. Okay, moving right along. A little bit more, there's more evidence that light behaves like particles. And this is Compton scattering, named after Arthur Holly Compton. If light behaves like a particle, then it should collide with electrons just like particles collide. Billiard balls would collide. And they do. You have to look a little carefully to see this effect, however. But here's the idea. This is the picture right out of the book. There's an electron sitting at the origin of this coordinate system, x, y. It's at rest initially, so it's just sitting there. And along comes a photon with wavelength lambda. Something happens, there's an interaction, and the electron goes flying off in some direction with a certain amount of energy at an angle theta, as you can see here. And then the photon bounces off and goes away, but notice it has a different wavelength. In fact, you can see it has a longer wavelength, right? It goes off at a certain angle. So there is a collision here, and it behaves just like billiard balls colliding. Mr. Compton wrote this down. He wrote down that the momentum of the incoming photon is h over lambda. He used conservation of energy and used conservation of momentum, just like we did last semester to solve this problem. He came up with this formula. So notice that the formula tells you the wavelength of the scattered photon detected at angle phi. Right, so if you put your detector here at a certain angle from this x-axis, you will see, different amounts of different wavelengths as you change the angle given by this formula. Is there something in the chat? I heard the ding.
Someone got kicked out, but they're back. So
They're back. Okay, welcome back. In fact, I'll take that as a cue to take the attendance. Whoops. Actually, let me finish this thought, and then I'll take the attendance. Okay, so if you do this experiment, you'll detect the scattered photons having different wavelengths depending on the angle that you look at, given by this formula. And the formula comes about by assuming that the photon and the electron just collide as if they were billiard balls. So further evidence that light behaves like particles. Now, if you look at this quantity h over MEc, right, that's the mass of the electron, that works out to be this number. So 0.00242 nanometers. That's called the Compton wavelength of an electron. Visible light is like 400 or 700, it's in this range over here, 400 to 750 nanometers. So this is tiny compared to that. You're not going to be able to observe Compton scattering using photons that are visible. Instead, you have to go to get photons that have wavelengths that are comparable to this distance. And that's up here. Right? This is 2.42 times 10 to the minus 12 meters. So that's somewhere over here. This is a graph, the spectrum with a wavelength on top. So we're talking about the upper range of X-rays and well into the gamma ray region. So very energetic photons. This is why it's not particularly easy to see Compton scattering unless you have those kinds of photons. Okay, pair production. Did you know that mass can be created out of thin air almost? This can actually happen. You could have a photon moving along, and all of a sudden it disappears, and out comes an electron and an anti-electron called a positron. It's just like an electron, except it has a positive charge. This is antimatter. This actually happens. However, it does not conserve momentum, so it can't just happen anywhere. You have to have some massive object nearby that can take away some of the momentum and allow this to happen. So the nucleus is here in this diagram from the book, because pair production on its own does not conserve momentum. And so if this is there and can be involved to take away some of the momentum, this can actually happen. And it does happen. Let's think about the energy. So the incoming energy has this energy, h times f, Planck's constant times its frequency. The outgoing electrons have energy given by E equals mc squared. Here's the electron. It has this energy, mass of the electron times c squared. And the positron has the same mass electron, c squared. So if we balance out the energy, we just say that hf equals 2 times mass of the electron, c squared. This is how you solve one of the homework problems. Okay, we got maybe 10 minutes to talk about the Bohr model of the atom. Here's another mystery from the late 1800s. A little water. Actually, before I do that, I'm going to take screenshots of attendance. Assuming I can get back to where we were. Here we go. Bear with me while I do this, please. Are people with me? Does anybody have questions?
I'm here, just listening.
I hope this is proving to be helpful. I'm kind of rushing through it, I know.
The book was not so helpful this week. It was a little dense.
Yeah, it's a lot to take in at first reading. So hopefully, I'm having a fun time as X-ray tech. Oh, cool. Yeah, exactly. So you deal with this stuff on a daily basis, I guess, or however often you work. Anyway, let's go right back into it. I have the attendance now. Here's another mystery from the late 1800s. Rarefied gases. So rarefied means that they're very thin. Their density is so low that the occurrence of atoms are rare. That's what rarefied means. So rarefied gases, when heated, emit light with discrete spectra. Why do you need a rarefied gas? Because then this emission of light can be attributed to individual atoms rather than some collective phenomenon. But anyway, take a glass container with a little bit of a particular gas, heat it up, and out will come light. But if you look at the spectrum of the light, it's not continuous. You have discrete colors of light that come out, discrete wavelengths of electromagnetic radiation come out. Why? That's one of the mysteries from the late 1800s. So if you did hydrogen, atomic hydrogen, so not hydrogen gas, atomic hydrogen, this is the spectrum that you would see, at least in the visible range. If you used helium, you would see a different set of light lines that come out. So remember what I'm doing. I'm heating it up. Light is coming out. I take that light and pass it through a prism to look at the spectrum. And this is what we see. There's only particular colors. And depending on what gas it is, I get a particular set of lines. As an aside, let me tell you that if you look at the spectrum of light that comes from the sun, you get, a nice rainbow. And this is in infrared over here, except that these certain particular lines are missing. Notice that this pair of lines lines up very well with this one. And this line lines up with that one, and this line lines up with that one. There are other details that maybe can't be explained on this diagram, but after examining this with care, you can explain why you are missing these lines in the light coming from the sun. This, by the way, is why we know that there's a lot of helium in the sun and hydrogen. And this is also how we know what gases are present in the atmospheres of distant planets. Like we know that, for example, there's methane in Mars. We know it by looking at the spectrum of light that comes and seeing that there are these missing lines that match up with what we measure in the laboratory here for methane or whatever gas. Okay, but anyway, these line spectra was a mystery. Measuring things very carefully for hydrogen, atomic hydrogen, you get this. The visible range is over here. And there are these different groups of lines like this that are named after people. Balmer was the first to do this. He's named after it because, so these are measured, but Mr. Balmer was actually a high school teacher who was, math was kind of a hobby to him. He noticed that these lines followed this mathematical relationship with m equals 2 for these lines here. That's kind of a fun hobby to have, right? Okay, so Mr. Bohr enters, and he created this atom model, which is sort of the mini solar system idea of an atom. You've got a nucleus, an electron that goes around. So the electron is in orbit around the nucleus, and so F equals ma. The force is the Coulomb force. Here's the mass of the electron. Its acceleration is centripetal acceleration, v squared over r. So he wrote this down. But that wasn't enough. And since quantum mechanics was in the air, what he wrote down, he imposed the quantization of angular momentum. Why? Well, that's just what he did. There's no time to describe why, but this is what he did. He wrote down the angular momentum of that electron and allowed it to be only integer multiples of this number here. So not a continuous angular momentum, but a discrete one. If you look at the book, you can follow through a derivation to get the allowed energy levels for that electron. You get a formula like this. And the book might express it differently. Here it is expressed in terms of epsilon 0, the permittivity of free space. But the bottom line is that when you evaluate this for hydrogen, this is what you get. Negative 13.6 electron volts divided by n squared, where n is an integer. These are the allowed energies for the electron. By the way, 0 energy in this formulation means that you have a free electron with no kinetic energy. Negative values of energy for the electron means that it's bound in the atom. Positive values mean that it's not bound and it's moving along with some kinetic energy. So the conclusion from Bohr's theory is that bound electrons can only have these energies. Negative 13.6, negative 3.4, negative 1.5 electron volts, etc. And note that unbound electrons can have any energy. Those are not quantized. So here's the picture. Here is Bohr's formula. And if you make a graph vertically of energy levels. Here's energy equals 0. The numbers predicted by Bohr's theory are the energies that are these blue lines here. And the theory then is that if you have these electrons, as they jump back and forth between these lines, between these possible energy levels, they give off photons. So in particular, if you've got a photon here, if you have an electron at this n equals 3 energy level, it might spontaneously jump down to the n equals 2 level and give off an electron a photon that has the energy equal to the difference between these two energy levels. And so it has a particular wavelength. Similarly for these transitions from higher energy levels, when these transitions happen, photons of that particular energy difference comes out. And that explains the discrete line spectra of hydrogen. This is what Balmer saw in the visible scene, these Lyman series and Paschen series. So those things are actually measured, as I said. This is what you see. Actually, this is what you see when you measure the spectrum of hydrogen. But if you're very careful about it and graph it versus wavelength, you see this. And these energies of the photons that come out with certain wavelengths are explained by the presence of these energy levels in the atom, given by this Bohr model. Isn't that cool? I think that's really cool. What's in the chat? Something in the chat?
I said that makes so much sense. I did not understand that when I did the lab this week. And then Julia asked, what do you mean by unbound and bound electrons? When you say unbound, do you mean the ability to go through one energy level to another?
Bound means that it's part of the atom. It's not a free electron that can go wherever it wants. It's stuck. Basically, it's married to the nucleus. So when an energy level is on one of these blue levels, down here below energy equals 0, it's part of the atom. When an electron has positive energy, it's not part of the atom. It's just flying along, going off to infinity or whatever. So that's the difference.
Is it still associated with that atom, though?
No, no.
Oh, okay.
If the electron has positive energy, it's gone from the atom. It's not part of the atom anymore.
Okay.
That's what it means to be bound. Okay, so that's it. I have a little summary of what photons can do. We talked about 4 things: photoelectric effect, transitions in the energy levels that we just talked about in the Bohr atom, Compton effect. They can act like billiard balls with electrons, and you can have pair production. The remainder of the slides, I have these problems worked out for you, and I also have a PDF of my handwritten solutions. I will leave them in for you to see later. But that's all I have for you, and I'm pretty much out of time. So I'll end there. I hope this was useful. I know you don't get a lecture. You're not getting a lecture this week, so I hope this served that purpose for you.
You are our lecture this week.
Yeah, I tried to pack everything in because in 50 minutes, at least introduce you to the ideas and hopefully make it easier to read the book for you.
Yeah, I think it will, having an idea before going back and rereading. The derivation of that one equation with the epsilon naught was really kind of confusing to look at, not having any previous exposure. So.
Okay. All right, everybody, have a good weekend. I'm going to have an office hour. I will post it. It might be later today, or it might, and it has to be if it's tomorrow. If it's tomorrow, it's late. Probably do both. Anyway, watch out for an announcement.
Thank you.
Bye, everybody. Okay, I'm going to pause, stop the recording.